Yes, class. Good evening. So in the last class, we had started with interference with white light. This was a very small topic that I asked you to write. So who all have joined? First, let me check. Amna, Deborah, Faiza, Tharif, Rajita, Shahid, Sidran, Father. All right. See, interference with white light, I told you that from a source, if entire spectrum of the rainbow, which we have entire spectrum of the white light, that is all the Vibgyor, all these colors are same, then in the center of it you will obtain a white light, and on the either sides of it you will be obtaining the entire spectrum of rainbow in exactly this order, in this Vibgyor order, this order from here, Vibgyor, this order, that is from here violet, indigo, blue, green, yellow, orange, like this. You will be getting like this here, and same thing you will be getting like this here. Now, the next topic that was left was intensity distribution curve for interference. We'll complete with interference. So one more thing, in Heinz principle, one topic is left. Reflection and refraction, how to prove through Heinz principle. That also we'll discuss. So intensity distribution curve. See, if you have bright fringes, and we have talked about the intensities, how to calculate the formula for the bright fringes, for the dark fringes, about the constructive interferences, destructive interferences, and how we have obtained the formula. Everything we have already discussed. Right. Now, see, if both the sources that are emitting these light, if they're having the same intensity, the intensity with which they are producing, it is exactly the same, that is identical coherent sources. Till now we have discussed that frequency should remain the same, wavelength should remain the same and all, but we didn't discuss that exactly the coherent sources have to have the identical intensity. This we didn't discuss. So if this occurs, then see, I1 will be equal to I2. So I will be equal to I under root I1 plus under root I1 will be 2 root I1 whole square. That becomes 4I. So this will be for the bright fringes. If the two coherent sources, both of the sources are identical as well, you have the same frequency, you have the same wavelength, but intensity we never talked about. Intensity could be different for coherent sources. But just in case if the intensity is also same, so it will be 4I, which will be the maximum. And what about the dark fringes? Dark fringes, I1 is equal to I2. If you write directly, they will cancel each other. This will be 0. This is for the coherent sources. And if you have the non-coherent sources, then intensity cannot be the same. For non-coherent sources, under I1 plus I2 plus 2 under root I1, I2, this phi will be variable for the non-coherent sources. Because for non-coherent sources, I have told you that for a source to be a coherent source, this has to have the phase difference, which has to be constant. So if phase difference is only variable, then the intensity, then this cannot be coherent, this will be non-coherent. That's why you do not have any specific equation for non-coherent. It can be variable depending upon the angle that is given. So if we plot the graph, this is how the intensity distribution curve looks like with coherent and non-coherent sources both. First, look at the coherent source. The maximum intensity that is possible is 4I for the identical coherent sources, right? So that's why this one, the maximum one is 4I. So this is for bright fringe. This one is, these are the bright fringes. Then you are having here exactly 0, which are the dark fringes. Then again the bright fringes at 4I, dark fringes at 0. 4I, 0. On the other side of the graph for the negative angles also 4I, 0. Here 4I, 0, and this will be moving on. But this is for coherent source. For non-coherent source, you see this is independent. It's independent. because phi is variable, so the entire graph you're getting this independently. All right, this is about the intensity distribution curve. Write it down. One good question I have that we'll discuss. Write it down first from here, intensity distribution curve. See, this says that a beam of light consisting of two wavelengths. One is 800 nanometers and other is 600 nanometers. This is used to obtain interference fringe in Young's double slit experiment on a screen placed 1.4 meters away. So if both the slits are separated by 0.28 millimeters, we have to calculate the least distance from the central bright fringe where both of these bright fringes will be coinciding. See, it's like this is the figure. This is the source, this is S1 slit, this is the second slit. Let's one is represented through red color, other one is represented through the blue color. All right. So red is coming, blue is coming, red is coming, blue is coming. Central maxima has been formed. Now we have to find other fringes will be formed, bright, dark, like this will be formed. And we have to find a point where both the bright fringes will be coinciding like this. Understood? Where both the bright fringes will be coinciding. So like this. Let's say the separation of one is yn, separation from this other one is ym, just for the differentiation. Because y, I have already told you, it is the displacement. Displacement of what? Displacement of the fringes from the central maximum. Understood? So this only we have to find out distance. It's just that yn is equal to ym in this question. This is the condition that has been given. So if we know the formula of this fringe separation from the central maxima, that is y, which we write it as n lambda capital D by small d. This is capital D. And this is written as the small d. This is the small d. So yn is equal to ym. So if this is nth one is coinciding, it means nth one is coinciding with mth one. So that's this we have to find. So nth one, that is lambda 1 capital D by small d. Both of them will have the same. This is m lambda 2 capital D by small d. Capital D, that is the distance between the double slit and screen, will remain the same, and separation between both the slits will be the same. So dd cancel. Now n is equal to lambda 2 is 800 nanometers, lambda 1 was 600 nanometers into m. So 0, 0 will be cancelled, nm will be cancelled, 8 by 6, n is equal to 3 by 4 m. Now we are stuck here. Class, there is no method, there is no formula left that we can further find out the answer. N is equal to 3 by 4 m. That's it, what we have obtained. Further, there is no equation which is left. We have no information about either n or m, and we are having two variables with just one single equation. We cannot solve it further. One thing that we can apply is, see, one thing we definitely know is number of fringes that will be coinciding or number of fringes formed. It will always be a whole number. N will be a whole number, m will be a whole number. Rather than it will be natural number, not a whole number. All these will be natural numbers. N will be either 1, 2, 3, 4, 5. You will not have a bright fringe formed at 0.25 separation. That nth is formed at the first, this is the first fringe. Then you have the second fringe, you have the third fringe, fourth fringe, fifth fringe, sixth fringe, like this you have. You will not have the first fringe, then 0.25 fringe, then second fringe, then 8.5 fringe, then third fringe, then 4 by 5 fringe, like this. No, all these will be proper numbers because these are blocks that are formed completely. So if I use the hit and trial method, if I say m is equal to 1, what is the value of n? N will be 3 by 4. This condition is not possible. If this is first, this can never be 3 by 4. If m is equal to 2, n is equal to 3 by 4 into 2, that is 3 by 2. Again, this condition is not possible. Why is it not possible? Because 3 by 2 of a fringe can never exist. 0.6 number, do you have ever? If I count the number of students in this class, I'll have a particular number. if the number of participants right now is 12, so it will always be a natural number itself. Or if nobody is there in the meeting, it will be 0. That is, the complete whole numbers will be there. But minimum, you have the natural numbers present at least. I'll not say 9.5 participants are present or 3/2 participants are present right now, because we have proper countings of it. Similarly, now m is equal to 3. So n will be 3/4 into 3. That is 9/4. This is also not possible. M is equal to 4. Now see, is it making sense? 3/4 into 4. 4 cancel. N is equal to 3. So M is equal to 4 with N is equal to 3. This means the third fringe of the... See, this means that fourth bright fringe of λ2 wavelength will coincide with third bright fringe of λ1. This is how you have to solve it. Write down the solution. One more thing, class. So today is the last day when this shifting of batches has occurred. The second batch students have come right now also, like Amna, Fadil, Deborah, all these students. And you people will also be coming in the second half, I have told you. So it's the last day now. From the next Saturday onwards, we'll be having the revision schedule you will get. So separate batches you will have, different schedule you will be getting for the revision classes from next Saturday onwards. Tomorrow we don't have any class. Today we'll try to complete the entire syllabus. Tomorrow will be an off for you, so just attend both the batches classes today. And for the Saturdays, you will be getting proper schedule for it. So students, you will be informed earlier this week only about your revision schedule. So you don't have to now come for extra classes, because extra classes I had taken only for completion of syllabus. All right, now let's start and complete this so that in the second half also it's completed. Beta is the fringe width of each fringe. The width of each fringe, this is known as beta, whose formula is lambda capital D by small d. That's it. So one question based on this. Do one thing, write down the question first, then I'll discuss this. Also write down the formula. Let's discuss this. So it says that light of wavelength, okay, wavelength is given 6000 angstrom in Young's double slit experiment. Separation between the double slit and the screen is 5, that is capital D is 5. Separation between both the slits, that is small d is 10 millimeters. Now you have to calculate separation of second bright fringe from central maxima. It means what do we have to find out? From the central maxima, whenever we have to calculate anything, we write it as yn. That is n lambda capital D by small d. And n is equal to 2. So lambda is equal to 6000 angstrom. This will be 6000 into 10 to the power minus 10 meters. Capital D separation is, and that was 10, no? 10 millimeters. Huh? 10 millimeters, 10 into 10 to the power minus 3 meters. So if we substitute the values, y2 will be 2, n is 2, lambda, 6 into, this is 10 to the power minus 7 into 5. This is 10 to the power minus 2. So 10, 3, 7, 4, 4 is left. This is 6 into 10 to the power minus 4 meters. Second says that separation of third dark fringe from central maximum. So n is equal to 3 and yn is 2n minus 1 lambda capital D by small d. So this question is a complete revision of the entire Young's double slit experiment and your interference. Here n is equal to 3. So y will be equal to 2. No, this will be 2 into n is 3. So 2 into 3 minus 1 into 6 into 10 to the power minus 7 into 5 by 10 into the power minus 2, which is 5. So 75 into 10 to the power minus 5 meters. Third part, fringe width. Fringe width, that is beta in lambda capital D by small d. So this will be 6 into 10 to the power minus 7 into 5 by 10 to the power minus 2. This is 30 into 10 to the power minus 5, which is 3 into 10 to the power minus 4 meters. Fourth part, angular fringe width. Theta is equal to lambda by small d. This also I have discussed with you. Lambda is 6 into 10 to the power minus 7. This is 10 to the power minus 2, which is 6 into 10 to the power minus 5 radians. Fifth, last part, fringe width if whole apparatus is immersed in a liquid of refractive index, n is equal to 2. So see, beta in any medium is equal to beta in air by n. Beta in air, we have calculated 3 into 10 to the power minus 4. This is 2, which is 1.5 into 10 to the power minus 4 meters. This is how you have to solve all the questions which are given. Write it down quickly. All these are very easy questions. See, these two derivations were left, which I wanted to discuss before we start with diffraction. So interference is over. That was all about interference. That question is very important because it combines all the concepts that are involved in interference, be it fringe width or any other topic. Now, reflection on the basis of wave theory, how will we prove it? So suppose this is our reflecting surface. This is the incident ray. All right, this is the incident ray. This is the incident ray. Look here. If this is the incident ray, with the normal, it will be having the incident angle. We have the wavefront perpendicular to the incident ray. I have told you that whenever we have wavefronts and rays are perpendicular to each other. So perpendicular to the incident ray, here is the incident wavefront. So from this plane surface, this makes the angle of incidence, that is I. All right. This is the angle of, this is the reflected wavefront, and this is the reflected ray. Again, this is forming the angle of reflection. Clear? Now, these are the perpendiculars that have been dropped on the wavefront just to obtain these triangles. So see, the distance here is taken as speed into time. So this is what Vt and Vt has been written. Why Vt? Just to make sure that the separations are same. That is this A dash and BB dash. Both of these rays are same. A dash and the BB dash. So this is Vt, this is Vt. Why Vt? Just to tell you that both of these rays are same. Both are making angle, subtending angle perpendicular. These are the rays that have been formed. So angle of reflection, angle of incidence, this is the rough surface, 90 degree, 90 degree. Now, why have we drawn the reflected wavefront like this? So see, from this point, one secondary wavefront has been formed because of Hines principle. Here is just the application of Hines principle. The rest of it is just geometry. See, for if you look at the A point will act as a fresh source of disturbance. So here a secondary wavelet will be developed, whose tangent is the reflected wavefront. Similarly, from point B, can you see these arcs? This is the secondary wavelet that has been developed. These are the new sources. That's what we have studied in Hines theory. That's how we have obtained the reflected wavefront. Perpendicular to it, we have the reflected ray, reflection angle, incident, and perpendicular lines. Derivation is very easy. In derivation, you have to remember, see, two triangles have been formed. All right. B, A dash. If this bigger triangle you look, let me write it down. B in triangle A dash. And triangle, if you look, B dash A. All right. A dash B was this triangle. And if you look here, B dash A dash. In both these triangles. Can you see these, both the rays are same? That is A dash is equal to B dash. Why? Because both are equal to Vt, which I was mentioning to you. This angle A and angle B, both are same because both are making angle of 90 degree, right? And this is the common side BA dash. BA dash is equal to BA dash, which is the common side. So triangle what was the name? B dash A dash is similar to triangle. This is similar to triangle A dash. So if both of these are similar, these two triangles are similar. This angle is equal to this angle. This side is equal to this side. This is the common side. This side and this side will also be equal. Also, this angle and this angle will also be equal of the triangle. That is, angle I will be equal to angle R. This proves the This proves the law of reflection. This proves the law of reflection. All right. We'll see wave theory also. Write refraction also. Write it down first. Okay, refraction on the basis of Hines theory. Now see, this is the incident ray, this is the normal, and the ray is getting refracted. Again, perpendicular to it, we'll have the incident wavefront. Now this A point will be giving rise to the secondary wavelet because this will be acting as a fresh source of disturbance, which we have seen in Hines theory. Then we have B point. B point will be also making the secondary wavelength that will be acting as the fresh source of disturbance. All right. Okay. So again, this separation is V1T, this separation is V2T. This time both are not VT. That's why in the previous question, I specifically wrote that V into T both are the same. Here velocities are different. So N1 is rarer, N2 is denser. So V1 is greater than V2. All right. So this is the incident wave front. This is the reflected wave. How reflected wave front has been constructed because of these 2 points. Understood? Now see, if again we start with the triangle BBA and we start with the triangle BA dash A, both these triangles. One thing, let's apply Snell's law at both these points, at this point and this point. In delta BA dash, sine I will be equal to, see here, if we're talking about sine I, this is equal to this triangle. If you see in this triangle sine I, because we have to further apply Snell's law and we have to prove Snell's law for refraction. That's why we have to include sine in our equations. So sine I will be sine theta. This is the perpendicular. So perpendicular, and this is A dash, that is perpendicular by the base, which is B dash. So sine I will be equal to A dash divided by B A dash, which we can write it as B1T divided by B A dash. In the other triangle, that was B dash A dash. B dash A dash. Sine R is equal to B dash divided by B A dash. This is equal to V2T divided by B A dash. So when we take up their ratio sine I by sine R, if we divide it, this will be V1T divided by B A dash. This will be B A dash divided by P2T. T will be cancelled. B A dash will be cancelled. This is equal to V1 by V2. Also, we know one more thing. One thing we know that V1 by V2 is equal to N2 by N1. So hence we have sine I by sine R is equal to N2 by N1. This proves the Snell's law. Write it down. Okay, now the last topic that is left in your entire syllabus is diffraction. So diffraction is what? It's basically the bending of light. Suppose this is the screen. This is an obstacle you have, opaque substance is present. So suppose light has been incident like this. Now see, when this light reaches the corner, there is a bending that occurs. This creates a shadow. You might have seen diffraction. If there's a corner, especially in the corners, a wide shadow is obtained in the corners. That is because of diffraction, because the light rays bend at the corners. So the phenomenon of bending of light around the corners of small obstacles or apertures and its consequent spreading into the regions of geometrical shadow. This is called diffraction of light. Basically, bending occurs around the obstacles. See here, the light rays path was straight. As soon as this object came, this bent, and here a shadow has been created. Write it down. Rest of the details of diffraction, derivation, and everything we'll discuss in the second half when you all will come. So after writing this, you can start leaving one by one. In the second half, please join. That will be the last class.